And I've been telling you that you need to select the best model for your data all the time. I've been saying that in every single lecture. So today I'm going to explain some possible methods that you can follow to select the best model for your data. Right? Let me check here. As you might remember, as I'm writing there, right? The idea of statistics is to reduce the uncertainty about the parameters, right? We have pieces of unknown information in our model, and we need to reduce uncertainty about it, right? We will always have uncertainty all the time, but we need to find a model that actually provides less uncertainty. That's the idea, and that's what science does, right? It's the rule for science in general. It applies to every single field, every scientific field. Also, you might remember that I told you that, hey, but there are a lot of possible models in the universe. And actually, there are many, right? Because data is random. That means that there is a random number, actually, of possible models in nature. But we are human beings, and we need to select the one that really works for our data, right? And even when we estimate the model and compare different models, we still don't know if that one is the best. There could be another one that is the best. But the only thing that we can do is to say, well, this is the best so far that we have. And sometimes in class, I'm gonna use, yes, it's kind of a weird meme, I know. That's what I thought at 12 a.m. You know, I was very tired. I was probably, I don't know. Yeah. So what is a fit or best fit model? And when I say the word fit, I mean that I'm estimating a model, right? When I say best fit, I'm saying that that model fits the data better or explains the data better. So I'm going to use those words, fit and best fit, all the time to mean like fit when I estimate the model and best fit when the model explains the data better, right? So, and why do I use those words? Well, because it's easier for me to pronounce and also because it's very common in statistics, right? Many statisticians will tell you, hey, can you evaluate the fit of the model? When people are saying evaluate the fit of the model, is that you have to evaluate how good is your model to explain the data, right? So, and you will read it a lot in stats books. The people will say best fit or fit the model, find the best fit of the model, or evaluate the fitting of the model, or how good is, or the goodness of fit is also another way to say it. So I'm gonna I'm gonna be probably saying sometimes, and you heard me probably in other lectures saying bad fit model, right? That means that that model doesn't explain the data properly, right? And it's not like is the worst model possible, but there are other better options for the data, right? And for this lecture, the main mantra that you should remember is this one. All models will always be wrong. All the models are wrong. But some of them are useful. And Box in 1976 wrote that. Well, he said it several times. And actually, you can see the reference here. All right. Let me move this bar. I have a big bar here. And I really hate it. Well, let's think about possible scenarios. Let me give you one possible model. So let's imagine that you want to predict depression, right? You want to explain how depression works. as always in this class, right? We always talk about depression and rumination and anxiety. I know. Very depressing in that sense, I know. I promise that in the future I will use more optimistic examples. But this is very close to what many students want to do here in this program, right? Many of you are going to be counselors, so you will be dealing with this topic. So in this example, I have a linear model, right? That's a regression model, the same model that we have been studying so far, right? And we have an intercept, we have a slope that is going to be the rate of change for self-esteem. Another slope, beta sub 2, which is going to be the rate of change for the relationship between I like pancakes and depression, right? And another predictor, and that predictor combination will have a slope, which is going to be the rate of change, right? And that one is going to be a combination, plus error, of course. There are things that we cannot measure. So, what do you think? Is this a good model? Do you think pancakes is something that should be related to depression? I don't know. Probably could be, right? I don't know. Probably you eat more pancakes when you are depressed. I don't know, right? It could be. I don't know. But to be honest, by looking at that, you might be thinking, probably liking pancakes probably is not the most intuitive predictor, right? Or I could be wrong. I haven't found any paper that says something about it, but if you find it, it would be nice to have it. So we can ask this question: would this model be better if I remove I like pancakes? I don't know. Let's see if that's better or not. Now, we will do it later, no worries. I want to explain something first. There is something that I haven't explained. Well, I mentioned very briefly, and I believe at the beginning of the semester. And and this something is something called the R square, right? The R square is very similar to what we do in ANOVA. Remember that in ANOVA we were doing the sum of squares that ended the last lecture, right? Sum of squares of the residuals, sum of squares of the model. Well, in regression we do the same, but we have a special estimate that will help us to understand better our model. And that one is something called the R square. The R square is the sum of squares of the model, right, divided by the total sum of squares of the data, right? And what we do is just to subtract one.
Let's talk about the new model.
No worries, it's fine. You can. What we do is just add one and subtract that. Why? Because by subtracting one, we are creating a number that goes from 0 to 1, right? It's a ratio that will go from 0 to 1. The closer it gets to 1, more variance is explained by the model. And why do we care about variance? Well, in regression, models that are good, or at least kind of good, will explain more variance. Models that are bad for your data will explain less variance. That means that overall, they explain less variability. And you might be thinking, variability on what? Well, on the dependent variable, right? For example, in this case, in this example here, it could be that my R square, let's imagine this, just here, R square. Let's imagine that this model has a square, R square of 0.05, which is very, very low. But if we remove pancakes, I don't know, probably the R square would be something like 0.90, very close to 1. If it gets closer to 1, it's a better model. So this R square will help us to select different models, which is nice. And let's an example. In the example, I changed pancakes for number of candies. I don't know why I did that. I don't know. Don't remember. It's the same concept. Candies, pancakes, yeah. They are sweet things. So the R squared will tell you the percentage of variance explained. So this ratio that goes from 0 to 1 can also be multiplied by 100. So if you have an R squared of 0.50, that means that you are explaining 50% of the variance or 50% of the variability, in this case, on depression, right? But let's see an example here. Actually, I'm estimating an example right here. In this model, I'm using depression as my dependent variable or outcome, right? And remember, we have an intercept. We have this slope right here, theta 1, another slope, and another slope. We will have a slope for each independent variable. That's how it works in regression. And once you estimate the model, of course, you will see something like this. So in this case, we can see that self-esteem actually is related to depression and is not explained by chance, right? The p-value is less than 0.005. So that means that, yeah, it's explaining something. Rumination, yeah, we know that rumination is highly related to depression and is not explained by chance. But let's take a look at number of candies. How many candies do you eat in 1 week, right? Well, the p-value is way larger than 0.05. And the slope is very close to 0, 0.03, right? So the rate of change is very tiny, right? It's almost a flat line. So you might be thinking, you know what? Probably number of candies can disappear from here. So let's take a look. In this model, I have an R squared of 0.42. Can I do it? So that means that 42% of the variance is explained by this model, the variance on depression, right? It's not that bad. It's not a bad model in psychology, to be honest. In psychology, we celebrate sometimes R squares of 0.20, right? In other fields, 0.20 is garbage. And in psychology, sometimes it's like, you know what? That's nice. At least you're accounted for 20% of the variance, you know? It's not that bad. So it depends on the field, right? This number also works like a correlation estimate. It's very similar. Remember that I told you at the very beginning of the semester that you could square the correlation and just interpret that as a percentage of variance shared between two variables, right? It's the same concept as the R squared. It's exactly the same. The R squared is actually a metric of correlation, to be honest. But in this case, we are accounting for the relationship of all the variables with the dependent variable, right? It's not only a pairwise estimate. Now, if I remove number of candies here, right, the estimates will change a little bit. But look at the R squared. The R squared is the same, right? When I remove number of candies, the R squared remains exactly the same. And you might be thinking, why? Well, I will explain why later. But first, let's do something else. Let's remove rumination instead of number of candies. Rumination has a big relationship with depression. So let's remove it. Let's see what happens. Oh, look at that. The R squared is now 0.05 without rumination. That is an important variable because it reduced the R squared. That means that now, without rumination, you are explaining 5% of the variability of depression, right? You are losing a very important variable if you delete rumination. But if you delete number of candies, Well, it doesn't matter because number of candidates is adding nothing to the model. It's just noise for the model, right? So number of candidates definitely should not be there, right? Because if I keep it or not, the R square is the same, right? So I should remove it because it's just noise. Sometimes you will have very wonderful hypotheses about how depression works. And you measure a lot of variables, but many of them are going to be garbage, right? So you have to select the best model that doesn't have any garbage in it, right? Any variable that is just pure noise. That's another thing that we do in statistics. We are more like noise detectors. We want to detect noise and isolate the noise and just get what is pure sound, right? So that's something that we do a lot in statistics. So when you see a large relationship between your predictor and your dependent variable, you also are facing a variable that explains a lot of variance. So you cannot delete that one. Now, let's take a look at the R squared. And the R squared can also work as an indicator of goodness of fit, the model. So a R squared that is very high, very close to 1, indicates that the model fits the data better. If the R squared is very small, like the one that I showed you, that was 0.05, right, without combination, that's a very poor model. It doesn't fit the data better, right? It actually fits the data worse, right? So this is what happens when you have a high R squared. With the high R squared, most of the dots will always be around this line right here. In here, what we are plotting is predicted values. And on my y-axis, what we are doing is actually plotting the actual values, right? The observed values in a standardized metric. And let me show you what happens when that R squared is very low. When the R squared is very low, look at the line, right? First, the line is kind of weird, right? It's not as steeper as the other one. Oh, let me just go here, right? It changes a little bit, that relationship. And also, look at the dots. There is no pattern, like a specific pattern around the line. They are everywhere. They are sparse everywhere. That's because the R squared is very low. That means that that line that you see there when the R squared is very low is not the best line for the data. When the R squared is high, the line is closer to the data, right? So that means that you can trust this model because the line of best fit is way more closer to those dots, right? All these little circles, they are observations, right? So the line should always be close to the observed values. In other words, the model has to explain the information that you have in your data. The model has to be close to your data. So the R squared will help you to evaluate how far or how close is your model to your data. And you might be thinking, hey, but still, look at these dots. They are still a little bit far from the line, right? Well, of course, that will happen. There is not perfect model there is no possibility to find a perfect model for your data, right? The only thing you can do is to find a less wrong model. So of course, some of the observations will be far from the line of perfect fit because it's not perfect, but it's the best that you have. The R squared can also be adjusted. And why should it be adjusted? Well, the thing is that the R squared can get inflated a little bit by just throwing random variables. Let's imagine that you have, I don't know, 50 predictors for depression. just randomly, with 50 predictors, your R-squared can be very high. And still your predictors can be trash, many of them, because the R-squared doesn't discriminate very well. What predictors are the best. So many times we adjust that by the number of predictors in the model. So as you can see, it's the same formulation of the R-squared, but we multiply that by the sample size minus 1, and then we divide that by the number of parameters, of course. First, we subtract the sample size and minus 1, right? It's just a correction that we do in order to account for the number of predictors. Still, this is not the best method to select variables, but it's one method to select variables. And many times when you don't have time to do more testing on your models, you rely a lot on the R-squared, and the R-squared might be the adjusted R-squared actually would be kind of a good evaluator for your model, right? If you don't have time or you don't want to fuss, you don't want to fuss with other methods, you could do this one as a screening method. Okay. Well, this is what I said before. Yeah. Many times researchers will use the R-squared as the only indicator for selecting models, which is fine in kind of when you are exploring the data, right? You don't know a lot about the topic or you don't know about the data that you have in hands. So the R-squared could be a good method. But yeah, as I mentioned in there, it's like doing a soup. Sometimes you are very hungry and you say, oh, I can throw something into the pot. Something good might happen, right? So I start throwing a lot of ingredients, right? I can add, I don't know, a lot of things, a lot of spices. And at the end, the product can be very ugly. You could eat it, perhaps, if you're very hungry, but that tastes awful if you don't think what you're throwing into the pot. Similar thing happens with the R-squared. The R-squared is like a big pot. And if you add a lot of variables, yeah, of course, the R-squared will increase just randomly, right? But it doesn't mean that your model is the best. So we will study other methods to select variables. There is something called the Akaike information criteria. This one right here. Let me just highlight it here. This one right here, Akaike information criterion. It's a very famous goodness of fit indicator. We call it relative fit. And you can go to this link if you want to know more about Akaike. He died a time ago. He was an amazing statistician. He was Japanese. And he created this fit measure that is awesome. And he opened the possibilities for other and similar fit indices in statistics. In this case, we are going to do something that is very interesting. We are going to penalize. There's going to be a penalty for your model by the number of parameters that you have in your model in this new fit measure, right? So as you can see here, what it's doing is this is a constant that he created using calculus and other tools. And then you multiply that by the number of estimated parameters, right? And we are going to use something called the log likelihood. We haven't studied a lot about likelihood because I should do it probably at the beginning with others in the next two. But in simple words, likelihood is one way to quantify information. Remember that I mentioned that in the probability density functions, when we see probability density functions, the y-axis is likelihood, right? Likelihood is another metric for probability. And how it works is that this provides the an indicate. Well, yeah, it's like information of your model. How good is your model to understand the data? So it's more like information, right? There is something called maximum likelihood as well that we haven't talked about, and we will not talk about because that's a more advanced topic. But just think about likelihood as the information that your model provides, right? So each model that you run will have a likelihood, and we're going to estimate the log likelihood, right, of that model. Well, you will not do it. R and Jamovi and all softwares will do it for you. So let's see an example here. Let's keep let's check this model again, right? The same model that I estimated before. Self-esteem, number of candies, and rumination as predictors of depression, and my intercept right here. Never forget the intercept. So in this model, I have 1, 2, 3, 4, 5. 5 parameters. Everything that is a Greek letter is a parameter. And remember, what is a parameter? A parameter is a unknown information in the model, right? So we don't know the values for beta. We know the values for self-esteem because we collected data about self-esteem. We have data in our data set related to number of candies and rumination, but we don't know the slope, right? So in this new fit measure, what we do is to add here the number of parameters. In this case, we would add 5, the number 5 right here, because it has 5 parameters. So what Akaiki is doing is imposing a penalty on this index, on this fit measure, by the number of parameters. Let's see an example here. Let's start with a very simple model. So in this model, and actually you can see the code here if you want. It's a lot of code and it's black. I don't know why it shouldn't be black. So it's kind of hard to see it. I didn't program that to be black, to be honest. I don't know what happened when I rendered the file. But the model is right here, but it's fine. You don't have to see it. But this is the table, this is the output. So let's compare this model versus other models right here. Let me see if I did it. Yes, right here. So let's start with a very bad model. In this model, what I'm doing is, let me just write it down here. I have depression. And depression is going to be explained by nothing. It has 0 plus 0 plus 0. The only thing that it has, actually, let me just write it down here. The only thing that we are estimating is the intercept in this model, beta sub 0. The rest of terms are 0. That means that we don't have any predictor in this model. So that's why in this table you see only an estimate for the intercept. And remember, when we estimate only the intercept in the regression model, that corresponds to the mean. It's just the average value of depression. So this table is telling me that the average value for depression is 10.44, right? That's the average score for the overall sample. And that's it. I'm just getting the mean. That's the worst model that you can have in statistics, because you are not assuming or you are not adding any information to the model. It's just the mean. So in this case, we can compare this model versus another model where I add rumination. Yes, again, rumination. And when I add rumination, look at the AIC value. The AIC value tends to decrease. It goes down when I add rumination. Without rumination, when it was only the mean, it was 1300 something, right? And now it's 1200 something. So that means that it goes down. What's the story here? How do you interpret the AIC? If the model has a lower AIC, the model is better. If the AIC goes up, the model is worse. All this story just to tell you that, right? So that's how you interpret these numbers. In this case, of course, rumination should decrease. The AIC value should go down because rumination adds information to the model, right? Now, for very big models, it's hard to do this by hand, right? Like adding one variable at a time and check the AIC, it takes forever. And in R, there's a function, and also Jamovi kind of does that too. It has a function that is called step AIC, and you could build your model automatically. But I need to explain two different approaches to model selection. You can start creating your models with a very simple model, right? With only the intercept. And this is 0. Big 0. There are no predictors here, only the intercept. And then, little by little, you start adding predictors. So in this case, you have beta sub 1 and x sub 1 here, right? And then the next model will have another one. Would be beta sub 1 plus beta sub 1, beta sub 0, which is the intercept. Okay. You have the previous variable and then the other, which is going to be beta sub 2, x2. And the next one is going to have another predictor, and another predictor, and another predictor. In other words, you are building up the model. You could do that. Let's imagine that you don't have any theoretical idea about your data. There is no theory, you don't know. And you want to follow just an empirical decision. So you allow, in this approach, you allow the data to talk to you. So in this case, you start with a very bad model, and little by little, you compare different models. We call this the forward approach or building up approach, right? Or you can do the opposite. You could start with a very big model. So let's imagine that you have, I don't know, another predictor here, beta sub 3, very hard for me. No. Beta sub 3 here. And then you start in the opposite way. This is going to be your first model, then this one, and then this one. So you could actually start with a very big model and trim the model, cutting the branches of the model, right? And you keep the model that is more parsimonious. So you select the model that has the best fit and is more parsimonious. So either way is fine. You can start from the bottom to the top, or from the top to the bottom, right? Similar to this, actually. It's similar to playing with Legos or blocks, you know? So you kind of are building up your model. Oh, I didn't want to do it. As I said, in R, you can use a function, step AIC. This function will compare all the possible models if you give all the possible combinations to the model, to the function, which is nice. So you can have, I don't know, 50 predictors, and the function in less than 1 second will tell you what is the best model according to the AIC value, right? What it does is to try to find the regression model that has the lowest AIC value. Remember that the AIC value has to be the lowest in order to conclude or make the conclusion that the model is better, right? You might be thinking, how do I normally do this? Well, I normally start with the worst model, and I build the model little by little. I don't do the opposite. I do the opposite, like with a big model, only when I have a very large data set and I care only about prediction. When I care only about what is the best model that predicts the outcome, yes, I start with a very big model and then I trim the model. But when there is kind of a theoretical background for my model, I start with the worst model possible and then I build up more variables, right? I add more variables for very small data sets. But for very, very large data sets, probably I would start with a very big model and I trim the model little by little until I get the best model. And you might be thinking, I will never have a very big model. Well, you don't know. Actually, I might give you a data set that's very big and you will have the task to trim it a little bit, right? That could be a very good exercise. And probably you can select the variables that you want, right? I will not actually tell you what variables, but you could add as many variables as you want and see what type of model you see that day, or which one is the best according to what you do. We can play with that later, probably one assignment. But yeah, in here, in this example, I'm going to use rumination, anxiety, negative metacognitive beliefs about rumination. I'm going to explain you what is that. Positive metacognitive beliefs about rumination, activation, and attention. Let me explain you what is this about a little bit. I always like explaining what is behind the data. The story is important. So metacognition, and I mentioned this in the first class, metacognition is the thinking about your thinking, your thoughts, the thoughts that you have about your thoughts. Is one way that we regulate, that we regulate our thinking, right? So you probably have this internal voice in your mind, right? And sometimes you're like, wait a minute, why am I thinking this? Why am I having this intrusive thought, right? Like for example, people with OCD, right? They have a lot of thoughts all the time, right? And one of the things that they have in mind all the time is thoughts about cleaning, many times, about how clean they are, right? So many times they are like, did I wash my hands? Did I wash my hands 5 times? Did I wash my desk 10 times? Because if I don't do it, everything's going to be dirty. So that person is monitoring their thoughts all the time. And they have this metacognitive feeling like, oh, I might have forgotten to do it. So I will stop driving and I will come back again and clean it again, right? So that happens constantly in their minds. They are monitoring their minds all the time. Of course, in OCD is more extreme compared to a normal person, right? In normal people, sometimes, I don't know, you might be thinking, oh, that guy looks good. Yeah, he looks nice. Hey, wait a minute, but I'm married. Shouldn't be doing this. Oh, I like him, right? So you're monitoring your thoughts. You have thoughts about your thoughts, and then you stop. Like, oh, wait a minute, I shouldn't be doing this, right? So you stop according to your values and your beliefs, right? Similar things happen when we are talking about depression. When people are depressed, they are like, oh, I really deserve to be sad. I feel bad. I'm a bad person. I should be depressed all the time. I should kill myself because I don't deserve to live, right? Normal people would say, hey, wait a minute. People who are able to regulate their thoughts, they would say, oh, no, wait a minute. Oh, it's not that extreme. I mean, I'm not that bad. Look at this. I'm doing this thing good. I'm bad at this, but I'm fine. But people with depression cannot do that. Everything's dark. It's very hard to get out of the dark feelings and dark thoughts. They cannot regulate all those thoughts and emotions, right? So their ability, their metacognitive ability to regulate thoughts is kind of broken, right? So that's why I wanted to test. Of course, it didn't work, but I wanted to see if I could ask about those beliefs, metacognitive beliefs. What do I believe about my thinking, right? Do I believe that rumination is good for me? Like, for example, if I continuously think about my depression, if I continuously thinking about my problem, is that good for me? Or is that good for how I feel? Or is it bad for me? Does it help me to solve problems? Or actually it's the opposite. It blocks the problem-solving process, right? So that's why my friend and I took this scale called negative metacognitive beliefs about rumination. I didn't create that one. Somebody else did it. It was some clinicians in England. And also they created the positive metacognitive beliefs about rumination. So it was evaluating negative and positive beliefs about rumination. And actually in this study, it was about what teenagers believe about their thinking, which was way more complex. When you're a teenager, you really don't think about it. So we were trying, well, probably they could. Yeah, well, it didn't work very well. But probably because the translation was bad and many other things happened. The other variable, the other predictor for depression is activation. Activation is about how aroused I am sometimes. And by aroused, I mean like activation of your nervous system is related to anxiety, right? You could stop and regulate consciously how activated you are, and you could actually be more relaxed. Some people are better at regulating their activation very fast. Other people are not. When activation is very high and you cannot control it, is, for example, when you are in shock, right? Something bad happened, an accident, and it's hard for you to regulate your activation. But for some people, their threshold for activation is lower, right? So I don't know, it might be the case that one day the person forgot to turn off the lights in the house and the person left. And that person starts panicking, like, oh, Jesus Christ, I forgot about the light. And he or she's activated all the time for something that is very minor. It's not that bad. I mean, you could come back later and just turn it off, right? So the threshold for activation is different. So I was trying to measure that in a self-report instrument. It didn't work as well. And attention is your capacity, your ability to, of course, isolate any source of noise and just pay attention to what you're doing, right? Regulate your sources, your cognitive resources, and pay attention to the task, right? Focus on the task. That didn't work as well. You will see it later. Well, probably in the regression, doesn't look that bad, but I was expecting to see better results. And that's why these data were teaching. Unfortunately, I did a lot of mistakes here. All right, so let's see how it looks like. All right, this is the result. This is the full model. In the full model, we can see that rumination has a slope that is not explained by chance. That means that rumination is related to depression, of course. Anxiety as well. Attention is also related, right? And we can see activation and negative beliefs about rumination. I haven't added positive beliefs about rumination. And you might be thinking, why these numbers are different? Well, because the variables were not standardized, right? Remember that I explained about C-scores? Like when you do C-scores, it's easier to interpret the output. Well, in this case, I didn't estimate C-scores. So that's why the metric is different. So for example, it's telling me that for one unit increase in rumination, depression increases 3.85 units. Given that the scale is different, I can only talk about units. I cannot talk about a specific metric. If I standardize the variables and just create C-scores, transform it into C-scores, this would be different. And we can do it later to see the standardized solution. Because sometimes you want to compare how big is the relationship of rumination versus anxiety, for example. But in this case, it's hard to tell because every scale has a different metric, right? That's the problem. That's why I love C-scores. And actually, I should have calculated C-scores here, but it's fine. The idea is not to interpret the output too much, but the idea is to see the logic of selecting the best model. Or I don't know if I did it. Let me check. Don't remember. If I did it, that's a big relationship. Let me double check. No, I think I did it. No, this is the raw score. Yeah, this is the raw score. Yeah, no, I mean, if this was standardized, this would be a huge relationship, which is crazy. It wouldn't be happening. Or it would be an estimation error. But now it's just raw scores. So in here, I'm using the function step AIC, and the function gave me the final solution. And it tells me that, let me just see, yeah, that a model with all these variables will have the lowest AIC value. That's what it's telling me. I started with a very simple model, a model where only the intercept was estimated. That's what I did. And then the function will add one variable at a time, and it will give you the AIC value. So when the regression model had the intercept plus the rumination variable, the AIC was this one. Then when the model had the intercept, rumination, and anxiety, this was the value. And at the end, if you add all the variables, this is the lowest you can get. So that means that all these variables are meaningful for your model, according to AIC. The lowest the value, better the model, right? Oh yeah, and this one doesn't have any predictor because this is the intercept. This is the intercept model only, right? It's just a mean. And let's go to a break. Let's come back at 11:10. So you can have a break. Yes. All right. So this is the code for the data set. And actually the code to open this data is here on this slide. More options to compare models. It's dark, but it's right here. It's right here. So you can open this from my repository, right? You just have to copy this line of code, and you will be streaming the data from my repository, like we do all the time in this class. So I wanted to share with you here the standardized solution. So what I did was to use the function scale. This will transform all my total scores, my raw scores, into C scores. So it's going to be easy to interpret the output.
So let me just get the estimated model. It is depression total explained by relation. Depression. Imagine what I'm doing. I'm not typing the name, I'm copy and pasting the name because I don't want any typo. You know that R is case sensitive. So what I do is to copy and paste all the time the names. And you should do the same. Otherwise, you will spend a lot of hours thinking that you did something wrong and you are looking for a mistake. And the mistake was just a typo, right? Remember, the R is very case sensitive. Attention. Here. I'm gonna press enter here because and the data name is rooming data. Wait, what? Right. Oh, yeah, that's fine. Yeah, it's fine. It's not.
I have the question.
Yes, tell me.
How come when you add everything and then the last, you put data equal rooming data with the capital D? That's why when we typing and then we type the lowercase, they don't come out with the same
You
result.
mean here? Yeah, let me just.
No, the last. You see the last data, the last.
Here, rooming
Yes,
data.
rooming data. You see the date will be capital D,
Not
not the lowercase. Why?
Because I created the name in that way.
Oh.
I was the one who decided the name.
That means we need to match the head and the tail.
Yes, exactly. For example, no, the idea is that if the name of your object is this one, you should keep the same name everywhere, right? You have to make a reference to the object because we are creating objects. So, for example, if the object is Jennifer, you should spell Jennifer the same all over your code, right?
Right, but okay. And
I don't know if I'm misunderstanding the question.
The capital, the question.
It's a capital letter.
Yes.
Oh, it was my decision.
Oh.
It was my choice.
That's why when when we typing, we're afraid of like if we copy and paste and will be factory. So, and then I just typing and then they come out when I run. And then they don't come out. And I said, what's wrong?
Yes. Yeah, no, and especially because in English, well, we can actually do that, but that's a way that we program in programming languages. I like omitting or deleting the space. So I don't say rooming space data because actually R doesn't understand that. So what I do is just to do capital letter where there should be a space, right? Like a separation between words, right?
Okay.
But that's how I prefer to do it. But you don't have to do it like that. You can follow any rule that is better for you. So let's see. Now they are standardized, and I wanted to see the slope and compare different variables. Now you can read this number like it was a correlation. This one right here, where it says estimate. This slope can be interpreted as a correlation. So the closer it gets to 1 or minus 1, the strongest is the relationship with depression. So in this case, rumination has a relationship of 0.36. And you can compare this slope versus the other slopes. So now it's easier. And we can see that rumination is the one that explains the most of the variance. Compared to activation, for example, or positive beliefs, for example, about rumination, doesn't explain anything, right? The slope is 0.07 compared to a slope of 0.36, right? So rumination explains most of the variance. And the next one is anxiety, right? Makes sense. And kind of attention too. Attention and anxiety are at the same level. And activation, and explains something, 0.14. It's like a correlation of 0.14. It's a partial correlation, right? It's partialized by the conditional relationship of the other variables, right? So when I say that this number is now similar to a correlation, I'm talking about in terms of interpretation, but it is not a simple correlation. It is a relationship that takes into account the variance explained by the other variables, right? So it's a more complicated type of relationship. And that's why we prefer regression. So you can interpret the slope of rumination after keeping constant the variance of the other variables. So you are controlling for the effect of the other variables. That's what we do in regression. So that number is way better than the correlation that you will get just with a Pearson correlation. The Pearson correlation cannot add more variables, right? So it's not taking into account possible explanations for your outcome. But regression is different. Regression is actually accounting for that. And in the output in R, you can see the R squared. This is the non-adjusted R squared, and this is the adjusted R squared, 0.40. So this model is very good, to be honest. It's explaining 0.41% of the variance. It's not that bad. I would say, I want to say that it was a good effort from me and my friend not time ago. It was in 2011 actually, and yeah, it was not that bad, right?
And as I said, I was expecting to see a larger relationship between negative beliefs and positive beliefs about rumination with depression. And look at that. It's only 0.10 and 0.07, and this one is almost 0. So the metacognitive part that I wanted to measure didn't work. Or the theory is wrong. I don't know. It could be my bad or something's wrong. Yeah, it smells like popcorn, right?
Smells like a cigarette.
Yeah.
Cigarette, right? Oh yeah, now cigarette, yes. Yeah. I believe it's the construction. They are probably smoking or welding. Yeah, I don't know. I was gonna say welding, but yeah, it could be smoking. Okay, I just wanted to tell you, well, to show you the standardized solution, the fully standardized solution. Okay, we were here. So as I said, I started with a very simple model, and now is a more complex model. And these are the marginal effects of each variable on depression, right? You can see that rumination, as we saw in the numbers, right? It has a steep relationship. The more you ruminate, the more you get depressed. In anxiety is the same, right? The larger your score in anxiety is also larger, is going to be corresponding to a larger score in depression. In negative beliefs about rumination, the slope is not very pronounced or steep, right? It tends to be flat, actually, a little bit here. So, and that makes sense because the slope is very small, right? It was 0. What it was? The standardized one was 0.10, and this is, yes, 0.10 is very small. So look at the line. The line tends to be, right, like almost flat. Attention is kind of a weird distribution because the way I scored, well, the way the scale was created,
kind of created discrete more like a discrete distribution, which is weird. So that's why I never did anything with this data. I never thought about it when I added this scale, but that's okay. So the relationship is negative. If I'm better on attention, my depression score decreases, right? If I'm better on focusing on things, my depression gets down. And that actually makes sense from a cognitive perspective, cognitive psychology perspective. Because if you're good at focusing on tasks and your executive function, I don't know if you know what is executive function, you probably were studying that with Garrick, I'm not sure. But if you're good in your skills in executive function, right, that means that you are good at regulating your thoughts, right? You can stop your thoughts. And by stopping your thoughts, you could regulate your behavior and regulate your emotions. Everything is connected, right? Emotions would have a cognitive component, right? And a physiological component. And everything is interconnected. And if you're good at regulating your thoughts, you're going to be good at regulating your emotions. So attention could be a good indicator on how you regulate your thoughts. So it kind of makes sense, right, that is happening. I was expecting a steeper relationship, and that happens because the attention scale was garbage. The activation scale is another one that is weird because look at these values. It's more like creating groups, right? It's very discrete. That shouldn't be happening, and that's how it happened here. And the relationship is very tiny. The slope is positive, but it's slightly positive. It's almost flat. And that makes sense too, because the activation slope is 0.13, right? They standardized 0.14. And it's very small compared to, for example, anxiety or rumination, right? They have a steeper relationship. The line of best fit is more going like towards going up, right? So, yeah. That's what we have so far. Okay, cool. Now, we can do the opposite. What we can do is to start with a very big model and then select the model that is more parsimonious. And that's what I did in this example. And let me just highlight this because it's very dark. And in fact, let me show you the syntax here. This is clear. So in here, this is the function step AIC, right? And what I do is to provide a full model. And then I tell to the function, hey, this is my full model, right? This is my big model. And here I'm specifying the worst model that I want. So it's like going from the top to the bottom. So I'm creating a big tree, and then I'm trimming the tree a little bit. So I'm telling to the function, I'm going to start with a big model and you have to go towards a very tiny model. And the tiniest model is the model that has only the intercept, the model that only estimates the mean. And I say go backward. That means start with a big model and then just cut it down until it's the simplest model. And what I get, let me see. Yeah, again, is this one. It's a model without positive beliefs about rumination. It dropped positive beliefs about rumination, and it kept all these variables together, right? Now, questions that you might have for this class with this topic. One question that you might have in mind is, well, how is he going to ask me about it? I mean, it's a lot of steps, right? A lot of things that I haven't done in my life. Okay, probably I will provide the code as always, right? I will provide the code where I teach you again and I remind you how to use the step AIC function, right?
Is this gonna be on assignment 4, which is our next one, right?
The next one is gonna be the number 2.
Okay.
Yes. The number 2/3. It's gonna be very long.
Okay.
Yeah, it's gonna be like 2 assignments in one, so we save time. Yeah. But yeah, it will have an exercise of several ones where you have to use the AIC function in R, and also you will be able to do it in Jamovi. I just don't remember how you do it in Jamovi. Let me double check. Do I have time?
Yes, I have time. Probably I should start from there, but I need to save the data. Just 1 second. I can just write down the data in the hard drive. Because Jamovi doesn't work like that. Send state documents. Okay. Directory. That's okay. Let's save it there. What I'm gonna do is to write the data as a CSV. The problem is that Jamovi will not open online links like I do in R, like this link from a repository. It's not possible to open online data in Jamovi, right? So I have to save the file in my local computer. And I might have it around there, but it's easier if I just save it. And I'm gonna call it like that. All right. Let me see if that works.
Are we gonna use Jamovi for the next assignment?
Yes. Both actually are Jamovi. Just because you have to learn this one. Yeah. It's not like the one that I like the one that I like the most, but let me see. That should or here. Yeah, right here. Okay, cool. Now the data is in Jamovi. And we do have the total scores right here. And they are C scores now. So they are at the end of the data set. And the way you select your variables, I believe, is right here. If you go to regression, and in here we are exploring together because I never do this in Jamovi. So let's see how it goes. Just move. Oh well, it's frozen. Nice. Jesus Christ, why? For some reason it doesn't want to go down. Look at that. I cannot go down. Let me just open again the data, I guess. Jesus Christ. Let me go here. Regression. Linear regression. Now it should work. Let's see. Oh, that is insane. Now it's working. I don't know why it's doing. Okay, so our dependent variable is depression. And let me see. Model builder. So I guess I need to add all the covariates here. I guess. Yeah. This is block 1. Can I remove? Yeah. So look at that. In order to do it, you have to add blocks. So the block 2 will have activation. We'll have the extra variable determination. Yes, this is block 2. This is model 2. And model 1 is here, only with activation. Then it adds termination. Then a new block adds negative beliefs, main effects. Now I have 3 models. Yeah, this is annoying. In R, you just have to just run one line of code and you have everything in one output. But in here, you have to do it by block. So you will have to do that probably. If you want to use Jamovi. It's going to be optional. You can use R or you can use Jamovi. It's up to you.
Will you like provide a video walking us through?
Yes, I will. Yes, I will. You know, even for me, this is just not the best way to analyze data. So look at that. It will give you the change in R square, right? So it's telling you if the model gets better or not, right? So 1 versus 2, the change was 0.30. So that means that the model got better, right? The second model is better. But the second model compared to the third model, yeah, it gets a little bit better, but the R square increases only 0.03 points. So it's telling you information about it. But let me check if it will give you the AIC. I believe it should. Yes, it's right here. But I don't see the AIC here. It's right here in this table. So this table is the summary of your models. So this is my first model, second model, and third model. And this is the value for the R square. And yeah, it gets a little bit better when I added negative leaves. But of course, negative leaves doesn't explain a lot, but still is better. The AIC goes down. That means that the model 1 is the worst, then the second one is better, and the third one is even better because the AIC value is smaller, right? So that's how you know that you're adding meaningful information to your model. If the AIC decreases in one of the steps, that means that the variable is useless, right? And the first model was a model where activation was the only predictor. Then in the second model, we added rumination. And then in the third model, we added negative beliefs about rumination, right? And yeah, adjusted R square. Yes, let's see that. Oh, that's interesting. Yeah, the adjusted R square could be negative. Yeah. And if you want this in a standardized metric, oh, we don't need it because they're already standardized, so forget about it. They're already standardized. But we did coefficient. Okay. Cool. Yeah, I don't like Jamovi, but you have to learn it because other instructors use it in this program. So you have to, if you want to communicate with them. So that's why. Otherwise, I would just teach everything in R. You will do everything in R. You should be fine. But yeah, that's how it is. So yeah, Jamovi provides the same information. The only thing that I don't know is how to estimate a model with only the intercept. Let me check. I don't know if it will allow me to do that. The intercept model only. Let me double check. No, it doesn't do it. Check. No, it doesn't do it by default. Yeah, well, that step cannot be done with Jamovi, probably. Yeah, it can only be done with R. It doesn't allow you to do that. Probably because we never test the intercept model only. We assume it's the worst and that's it. But for the sake of learning, it's better to do it. Well, that's how it is. And let me come back here. Did I add that one? No. Okay. Well, that's everything for today. I went very fast on this. So watch out for the assignments. And yes, I'm going to create videos on Jamovi, unfortunately. So
When is the assignment going to be posted?
probably Sunday, Monday.
Okay.
Around there, but I will give you plenty of time.
Okay.
I always give you like 2 weeks to finish everything.
Okay.
So it should be fine. Yeah, even need more time, but remember, don't actually wait too much. I mean, don't put off things for a very long time. Because everything will accumulate, and if I don't have your material by the end of the semester, I have to put a 0 there. And I don't want to do that. So
When we post the assignment, will you have this video?
it will have a link to the video. If there is a video, you will see a link. If I don't have time to do the video, I will. Because that one requires a specific video. Yeah, no, that's okay. I will do it. Yeah. Thank you.
Need that video.
Yes.